Right. Now, if all the protons were the same, right, we would end up with just one signal. And that's not going to be too useful to us in terms of solving a structure or getting any information out of that. If all the protons behave the same, we'll just see this one signal here for every sample that we have, and we can't actually say which is which or what is the structure, etc., etc. So there must be differences in the energy involved that flips the alpha state to the beta state and decays back again. So there must be slight differences that allows us to see resonances throughout this continuum. And generally you'll see resonances from about 0 to about 15, right? 15 ppm. So from 0 ppm to 15 ppm, you'll see resonances in the spectrum. So there must be slight changes to those protons that will allow that. So this brings us to the concept of shielding and chemical shift, right? So generally what I mean by chemical shift is where in this plot do I find the signal? Do I find the signal at 1? Do I find the signal at 3? Do I find the signal at 4? And what does it tell me if I find the signal at 1 or 3 or 4? What does it tell me about the environment of that proton? Can I get information about the environment of the proton? And can I use all that information to ultimately get the structure of a molecule? All right, so let's spend a little bit of time talking about shielding. But before I do that, I'm just going to stop for a while to see if there's any hands. I've got a hand here from Ngosingapile Badebe. You want to ask a question? You're on mute at the moment. Maybe you can unmute yourself.
No, sir, I don't have a question, sir.
Good. Okay, so I'm just going to lower your hand. Is there any other questions from the class at this point in time? You can just shout out if you have a question or you want me to clarify something. If there's nothing, Noor Mustafa, go ahead.
Hello, sir. I was just wondering if you could please re-explain that last part with the frequency, because I just got a bit confused.
Sure, definitely.
Thank you.
All right, so let me just re-explain this. So what happens when the nucleus gets excited to the beta state is that that's a very high energy state. So that energy will be lost to the surroundings. And as that energy is lost, it doesn't have that energy anymore, then it's going to have to go with the flow of the applied magnetic field. And that's going to be the alpha state, right? So this is called a free induction decay, right? And this is intensity versus data or time data. We convert that to intensity versus frequency. So the FT, the Fourier transform, converts that time data into frequency data. And that frequency data is related to the energy that's needed to flip from the alpha state to the beta state. And this frequency is actually what we plot onto the NMR spectrum. So we're not plotting the time data like this, right? We're using a calculation, and this calculation that we're using, we're going to now plot that onto this graph. So can you see, as the energy changes with the different protons, we're going to get different amounts of energy. We can see different signals that we can actually have in this particular spectrum. And that's why we can get peaks throughout the spectrum and not just one peak at one possible time. Good, so I hope that clears it up for you. Great, so I'm going to move on to this important concept that we have of shielding and de-shielding, right? So basically the chemical shift is just where on that graph do we find a signal. Now, in molecules, you don't just have free protons. I've been talking so far about a free proton, right? Just hydrogen. And I've not been talking about a molecule. Now, in a molecule, you have a carbon-hydrogen framework, all right? So you've got hydrogens bonded to carbons, bonded to other carbons, bonded to other hydrogens. So you have a network of nuclei, and you have a network of electrons holding those nuclei together. And that's what gives you a molecule, right? So if you're looking for a definition of a molecule, I don't know what they taught you in first year, but it's basically a bunch of electrons and protons held together, right, by electrostatic forces. So the electrons hold those nuclei in places, right, in their own specific places that give them the structure of that molecule, right? So these are bonds that you learned from first year, sigma bonds and pi bonds, etc. Right? So the proton nucleus then is embedded in this cloud of electrons, right? Now electrons, as I said, also behave as magnets, right? And they can shield the nuclei from the applied magnetic field. So what do I mean by shielding the nuclei from the applied magnetic field, right? If you are playing cricket, right? You're wearing cricket pads. When you get hit with a ball on your cricket pad, that cricket pad now shields your leg from that cricket ball, which is hard, right? If you didn't have your pads on, you'd feel the full effect of that ball, of that cricket ball, and you probably get hurt in your leg, right? So I can probably safely say that the cricket pads that you have will shield your leg from the full effect of the ball when the bowler bowls the ball, right? In the same way, the electrons shield the nuclei from the full effect of the applied magnetic field, right? And how does it do that? The electrons induce a local magnetic field. Remember, I told you that electrons are also spinning charges, although they're much, much smaller than the protons. Remember that a proton is much larger than an electron. You learned that in first year. How many times more? About 2,000 times larger, right? So the proton is much larger than the electron. But this small electron that we had, so if I said that the proton had a micromagnetic field, imagine how micro is this, electron that's producing this magnetic field. But nevertheless, it's producing a small magnetic field, right, that opposes the applied magnetic field, right? So if the full force is coming with the magnetic field, these electrons can reduce that energy somewhat, right? And so what the proton actually experiences is not the full applied magnetic field. The proton experiences what we call an effective magnetic field. And that effective magnetic field just depends how much of electrons are around that particular nucleus to shield it, right? Remember I said that the electrons produce its own magnetic field in opposition to the applied magnetic field. So I can calculate what the local magnetic field is, subtract that from the applied magnetic field, and probably see what the nucleus is going to actually experience, right? So that's the effective magnetic field that the nucleus is actually going to experience, not the full magnetic field. If there's no electrons involved, I can take this part of the equation out. I can take this local magnetic field out because there's no electrons involved. And then my effective magnetic field will be the same as the applied magnetic field because there's no shielding. So this is without pads. I don't have any cricket pads on. So my effective magnetic field is going to be exactly the same as my applied magnetic field. And then I'm going to put some pads on. I'm going to put a thin pad on. My effective magnetic field might be a little bit more. I'm going to put thicker pads on. And if I put thicker pads on, I subtract more and more. And you can see this effective magnetic field gets less and less. So the greater the electron density around the nucleus, the lower the effective magnetic field, right? So the greater the electron density, the lower the effective magnetic field, and the less the energy is. So I need less energy to be converted from the alpha state to the spin state. So to the beta spin state. From the alpha spin state to the beta spin state, I need less energy because this local magnetic field opposes a lot of the applied magnetic field. All right, so the greater the electron density at a nucleus, the smaller the effective magnetic field, and a smaller energy would be needed to flip the spin. I spent some time talking about flipping the spin from the alpha state to the beta state and relaxing again. All right, so in an electron-rich environment, we say we have a shielded environment. Remember, you got your pads on here. And if the nucleus is electron rich, I've got a lot of electrons around my nucleus, we say it's shielded, and this is the upfield region of the spectrum, right? That's the upfield region of the spectrum. If we don't have shielding, if we don't have electrons, so now maybe I've got 3 pads on and I'm taking my pads off one by one. I'm experiencing more and more of the applied magnetic field. And if I experience more and more of the applied magnetic field because of the electron poor environment, we call that de-shielded. Here the pads are off, or the pads are coming off slowly. You see that as I go from here to here, the pads are coming off slowly, and slowly the pads are getting thinner and thinner and thinner. I'm experiencing more of the applied magnetic field. So in order to flip the spin, I need more energy, right? Because there's more of the applied magnetic field that I'm experiencing. So my effective magnetic field is greater as I go from 0 to 10 or 12 or 15. And then I can say that this is my de-shielded region. As I move from 0 to 10, I'm moving into the de-shielded region or the downfield region, all right? So which means that the electrons are very responsible for where I'm going to see a peak in this NMR spectrum. Whether I see it here, where there's a lot of electrons around the nucleus, or whether I see it down at 10 or 11, where there's less electrons around the nucleus. Right, so why would one proton have more electron density than the other? Right, so we've got 2 peaks, one in the shielded region, where there's a lot of electrons around it, and one in the de-shielded region, where there's not so much electrons around it, so it experiences a full force of the applied magnetic field. What would cause electrons now to leave? So what would cause my pads to be taken in somewhere else? Maybe the other batsman came and said, you know, I want to use your pads and take my pads out. So electronegative atoms would draw electrons from the nuclei. So if we get an atom that likes electrons more than the other atom with the electrons, and generally it's the proton that has electrons around it. Now generally protons don't like electrons too much. So if anything else comes and say, you know, give me your electrons, I like your electrons, they're going to say, welcome, take mine, you know, go ahead, take my electrons, I don't mind. So if there's any other electronegative atom, it's going to withdraw electrons from those proton nuclei and lead to an electron poor environment. An electron poor environment is actually a de-shielded environment where I'll find the signal downfield, right? Remember that occurs because we now have a smaller local magnetic field by the electrons, because the electrons are not so close to the nucleus anymore, it's a bit further away, right? And once we have a smaller B local, we'll have a larger effective magnetic field and hence more energy, and the signal will appear downfield, right? So generally what we're looking at, we're looking at any atom in the vicinity of the proton that can withdraw electrons. So if I see a signal here, immediately I know now that in this particular proton environment, I don't really have electronegative atoms too close to this particular proton, right? So I can actually have some information about this particular proton in the molecule, that in this particular proton's environment, it doesn't have electronegative atoms. Compare it to this signal here. So this signal that we get from the NMR spectrum, and if I look at this proton signal, I can say that this particular proton has electronegative atoms somewhere close by in this vicinity of this nucleus, because those electronegative atoms are probably taking electron density away from the hydrogen, leading to a higher effective magnetic field, and that's causing it to be downfield, right? So generally here, no electronegative atoms close by. Here, I have electronegative atoms close by. I can now start to get information about it. And as I go from 0 to 10 or 12, I can see that if a signal appears here, there's more electronegative atoms here than here, or here than here, right? And there's more electronegative atoms at 4 than 3 at 2, right? And I can say that there's less electron density around this proton than the other proton. So shielding is the first thing that allows the resonance to go on this scale and to have varying positions on this particular NMR scale and to have different chemical shifts, right? That is what shielding is all about. And the last thing that we're going to talk about is diamagnetic anisotropy. So diamagnetic anisotropy is another reason why we will get signals shifting from naught and this time to about 5 or 6 or 7, right? Notice that the shielding and deshielding effects with regard to atoms occur for about 4 to 5 maybe, right? Past 5 to 7, you're getting other effects. And this other effect is called diamagnetic anisotropy. Now, what is diamagnetic anisotropy? Let's attempt to explain this. This has to do with electrons again, but now these electrons are free to move in response to a magnetic field. And you know that your sigma electrons don't generally move, they're not free to move. So sigma electrons are responsible for the bond taking place between two atoms. We have some other electrons called pi electrons that you'll see in a double bond where you have 2 sigma and 2 pi, or you'll see in benzene where you have 6 electrons in a ring, right? And 6 pi electrons in a ring. And these pi electrons are able to move in circular motions, and they can move around the bonds. And when they move around the bonds, they also create an induced magnetic field, right? So we have the applied magnetic field, and we've got the magnetic field of this proton, and these electrons create an induced magnetic field. And if I look at where the proton is located, and I look at this induced magnetic field that's caused by the 6 pi electrons in benzene, where this proton is located, the magnetic field is aligned with this applied magnetic field. The same thing here in an alkene. Where this proton is located is aligned with the magnetic field. So in benzene and alkenes, the induced magnetic field, where the proton is located very importantly, because there's other protons like in porphyrin rings, where the proton is located somewhere here, which is against it, right? But in benzene and alkenes, the induced magnetic field where the proton is located is in the same direction. Can you see the same direction here as the applied magnetic field, pointing from south to north, pointing from south to north, pointing from south to north. Is in the same direction as the applied magnetic field. So the effective magnetic field is much larger. It's equal to the applied magnetic field, and now we're adding some induced magnetic field to that. So we're getting a much larger magnetic field, which means that more energy is needed now to flip the spin, and hence the protons appear downfield. All right, so generally we find the resonance of protons in alkenes around 5.5 to 6.5, and the benzene resonances, we find them from about 6.5 to about 7.5 or so, or maybe 6.5 to 8 sometimes. But and that depends on the environment. So this last slide that I have here just shows you the effect of what I just said, all right? So you notice there's my protons here, my 4 protons here, and I'm looking at the resonance of these 4 protons around that carbon. And that's the methane molecule. This proton resonance, and all these 4 hydrogens are the same. I'll talk about equivalence in the next lecture when I see you on Wednesday. But these four protons are the same, and this resonance appears at 0.23, right? There's my 0 here, that's 0.23. So this is my shielded region of the spectrum. Remember I said as I go downfield here, then it becomes more and more deshielded. So let's look at the next one. I'm taking one of the hydrogen atoms out, right? I'll take one of these hydrogen atoms out here. I'll replace them with this tetramethyl carbon that you, sorry, this trimethyl carbon that you have here. And what you notice now is that this carbon is more electronegative than hydrogen. So This electronegative carbon, right, in relation to this hydrogen, takes electron density now away from these hydrogens. So if one carbon's electronegative, right, it takes electron density away from these hydrogens. Can you see the effect it's having? It's moving the signal from there to there. They're experiencing more of an effective magnetic field, right? That's why the signal moves from there to there. What happens if I take the other hydrogen out, replace it with another carbon? Now I've got two carbons that are more electronegative, and they take away electron density from these two hydrogens here. So you see it moves, the signal moves from 0.89 to 1.13. And finally, if I take another hydrogen out and I replace it with a carbon, now I've got this proton which is bonded to this carbon. I've got that carbon, and that carbon, all taking electron density away from the hydrogen. You see the signal move to 1.41. So as I replace the electropositive hydrogen with a more electronegative carbon atom, 1 here, 2 here, 3 here, I de-shield the signal, and the signal goes from being upfield to downfield. So you can see exactly what I said in my lecture. You can see it in a real example here. But look at this resonance. This is 2.47. And here I have a nitrogen next to my protons. So the nitrogen is bonded to the carbon where the protons are. And nitrogen is much more electronegative than carbon. And if nitrogen is much more electronegative than carbon, can you see the effect? Instead of a 1.41, I'm getting a 2.47. So a carbon with 3 hydrogens. Then I've got a carbon with 3 hydrogens. When I had the carbon group around it, it was 0.89. Now when I got the nitrogen around it, it's 2.47. Can you see the effect of de-shielding here because of this electronegative nitrogen? I'm taking the nitrogen group out. I'm putting a chlorine in. Chlorine is much more electronegative than nitrogen. And see the signal going from 2.47 to 3.05. Oxygen is much more electronegative than chlorine. So I'm taking the chlorine out, putting a hydroxy group with the oxygen in there. That takes electron density from the hydrogen. And see my peak now, 3.39. So as I add on electronegative atoms, 2 bonds away, right? Can you see 2 bonds away? Because hydrogen to carbon, and that's so. This is 1 bond, and then another bond to the other carbon, right? So there's 2 bonds away. So the first bond is to the carbon, the second bond is to the other atom, and that's my carbon atom. So the first bond for this hydrogen will be to carbon, the second bond will be to the chlorine. So an atom 2 bonds away, which is electronegative, is going to de-shield the signal from 0 right up until about 4.55, depending on the electronegativity of the atom. Right, and this table you'll find in your books, and this table will actually show you where the different resonances are. So remember this, because of the benzene ring, that's diamagnetic anisotropy, right? And then diamagnetic anisotropy can be applied to the methyl group here. So the hydrogen bonded to the carbon bonded to the aromatic ring. When the hydrogen is bonded directly to the aromatic ring, see how big the resonance is, 6.5 to 8 that I told you about because of diamagnetic anisotropy, right? But if I compare this methyl group of 0.85 to this with a benzene ring, this diamagnetic anisotropy has an effect from there to shift it from 0.85 to 2.3. Again here, the diamagnetic anisotropy shifts it from 0.85 to 1.7. And I showed you as I add more carbons, how the signal gets down de-shielded, right? So you can actually have a look at this particular table in your textbooks, and you'll see the different chemical shifts and how the electronegative atoms, can you see here the bromine, the chlorine, the fluorine, how it affects the hydrogen bonded to carbon. See, fluorine is the most electronegative out of all these atoms, all the halogens. So it de-shields the hydrogen a lot here, and the resonance appears between 4 and 4.5. All right, good. And I'll give you this pack. I'll email this pack that I have to lecture you on today, so you can have it in your notes as well. I've just put the last slide here where you can see I took this diagram from your textbook. You'll also find it in your textbook. It shows you diamagnetic anisotropy. It's a better drawing than mine, and shows you how the magnetic field where the hydrogen is located is with the direction of the applied magnetic field here and here. All right, and I'll discuss equivalence and integration with you in the next lecture. So I'm going to stop sharing there and take any questions. I've got one hand. No hands. But if there are any questions, you can put your hand up or just shout out and ask a question. Good, so I hope I haven't scared you away from organic chemistry and scared you away from second year Chem 220. I'm sure you're going to get into the groove of things. You're going to like it a lot. As I say, I really enjoyed it. I've been an organic chemist now for over 25 years or so. I really enjoy what I do, and I'm sure that you will actually enjoy it as well. So thank you for joining me today for your first 2 lectures, and I will see you bright and early on Wednesday morning for lecture number 3, where we're going to talk about equivalence, and we're going to talk about integration of the NMR spectrum. Thank you guys, and have a good day further. Bye-bye.